Okay. Hi, everyone. This module is about training deep neural networks. Specifically, we will cover the practical techniques that make gradient-based optimization work well and converge to a good, stable solution. Right. So in the previous sessions, you would have learned about perceptrons, MLPs, forward propagation, back propagation, activation functions, loss functions, gradient descent variants, and so on. Now, all of these give you the tools to actually start training a neural network. But practically, when we do training, we might face a lot of struggles with the gradient-based optimization process, right? So, what can we do to ensure that the optimizer does not struggle? Right. So, we'll cover four topics. The first one is the initialization. How do we initialize the weights in a correct manner? The second thing is the gradient signals. How do we ensure that the gradient signals are, stable throughout the training? And then how do we normalize the activation functions, and these normalization techniques we'll talk about that can actually help us stabilize training by modifying the loss landscapes. And finally, we'll also talk about how do we make the network converge to a generalizable solution rather than overfitting to the training data particularly. Right? Okay, so let's start with the first part, which is on initialization. Okay. So why does initialization matter, right? So here's the core issue. In a deep neural network, each layer takes its input, multiplies them by weights, applies an activation function, and then the result is passed on to the next layer. In a deep neural network, this happens 50 or 100 times, right? And what we would want to know is that are the inputs and outputs to each of these layers actually well distributed, right? So this is what would be the term that I'm calling here as the variance of activations, right? So this is the quantity that controls essentially the factors that is compounding multiplicatively across subsequent layers, right? So here you can see that the variance is equal to the number of layers into the variance of the weights into the variance of the activations for the layers before that, right? So the main factor, multiplicative factor that you can see that's compounding this is the number of inputs into the variance of the weights at each layer, right? So what we would like to do is we would like to have this sort of feature, this factor constant. So here, let's look at a few examples, right? What happens uh, to this factor? So if this factor is less than 1, then you can see that the variance of the activations, when we keep multiplying, it would collapse to 0. Similarly, when the activation is greater than 1, then it's when you keep compounding multiplicatively, like say 1.1 power 50 would become 117, right? So you can see it exploding. So this would cause saturation. And when the variance is constant, this is similar to what we would have where the activations are well distributed across each layer, right? So to maintain stable gradients across all layers, we want to initialize such that the variance of the weights is equal to 1 by the number of inputs, right? We just take the n to the other side. Okay. Now, this is the main condition. This intuitively means that the more inputs that are feeding into a neuron, the smaller we want each weight should be. Because all those inputs get summed together, we want them to be equally distributed across all the weights. Okay. Now we talked about this n, the variance being 1 by number of inputs, right? It's a simple version, but the exact correct variance that we should be using depends also on the activation function itself, because each activation function transforms the inputs differently. Now, for a tanh or a sigmoid, we use something called Xavier or Glorod initialization. Here, the variance is 2 by number of inputs plus number of outputs, which accounts for both the forward and the backward pass. So why does tanh work with this? Because near 0, tanh almost behaves like a straight line with slope 1. So it passes the signal through as is without changing it, right? Now for ReLU, if you see, we use something called He initialization or K-Ming initialization. Okay, so here the variance is 2 by number of inputs. So why do we have a factor of 2? Because ReLU zeros out all negative values. Okay, that means on average only half the neurons are outputting something, right? So this factor of 2 compensates for that halving. So one important thing to note here is that the initialization should also depend on which activation function we are using, and we should ensure that these are matched. Okay. Now, in the next section, let's talk about how do we maintain the gradient signal to be stable, right? So in the first section, we talked more about the activation variance, right? So this is all related to sort of forward pass, but the same problem occurs during backward pass as well when you're computing gradients, because if you remember the chain rule, right? So if you look at this equation, the gradient for the layer 1's weights is a product of the L minus 1 factors before it, and each factor involves the weight matrix at that layer and the derivative of the activation function, right? And if each of these factors is slightly less than 1, say 0.9, you have 50 layers, 0.9 power 50 is about 0.005, so the gradient is sort of effectively disappeared, right? So, this is the main issue. And if you think for an early layer, we are chaining the partial derivatives from the output all the way back in a deep neural network, right? So when you're a product of many terms, if the factor is slightly less than 1, then the initial layers are not even learning, right? On the other hand, if the factor is greater than 1, then your gradients start exploding, right? And the loss diverges to none. So how do we fix these issues, right? So there are 4 practical solutions. The first one is a straightforward solution called gradient clipping. So here, when the gradient norms exceed a certain threshold, we just rescale them to a maximum value, right? It's pretty straightforward. It fixes the exploding problem, but it does not fix the vanishing problem. The second one is using another activation function. So here we use ReLU activation. So ReLU has a gradient of 1 for all positive inputs, right? So if you compare this with a sigmoid where the maximum derivative is 0.25, that's even for an active neuron, there's sort of a 4 times shrinkage as compared to ReLU. Whereas in ReLU, if the neuron is active, there is no shrinkage because the maximum value is 1. The third kind of solution for gradient instability is a normalization, which is batch normalization or layer normalization. This essentially recenters and rescales the activations at every layer, right? So we'll cover normalization in more detail later. The fourth one is also something called residual or skip connections. Here we simply add the input directly to the output, right? So the output y is equal to f of x plus x. And here when we take the gradient, even if the gradient of f of x tends to 0, the derivative of f of x tends to 0, when we take the derivative of x, we get the identity, and the identity is always sort of non-zero, right? So there is still a path for the gradient to flow through, even when the derivative of f of x becomes 0. So this is sort of a key innovation, and this is the key idea behind networks such as ResNet, which enable to go very deep without sort of losing or without this gradient vanishing problem. Okay. This is on gradient instability. The next section we'll talk about is normalization, which we also mentioned is useful in stabilizing the gradients, right? Now, apart from this gradient instability, there's a lot of other issues that you will start seeing when you start training, right? Imagine you have proper initialization, you've used ReLU activation function, and you've also implemented, gradient clipping and residual connections, so on. You might still observe a few things, right? So some of them are you would require to have very small learning rates, right? Increasing the learning rate even slightly starts causing the loss to diverge, right? So the convergence is very slow. Second thing is you'll have to initialize very carefully. Small change in the weight initialization causes a completely different solution. So this network is not very robust to initialization. The third thing you might notice is, adding deeper layers makes it worse. Even though you'd expect it to have more capacity, you see that, deeper networks become harder and harder to train. And the fourth thing you might notice is that the loss sort of, is oscillating unpredictably. So instead of the loss sort of going down or descending smoothly, you see that the loss curve is sort of noisy and jumpy, especially in sort of early epochs. So root cause behind all of this is that the optimization landscape itself is poorly conditioned, right? It might be steep in some directions and flat in others. So small steps are, safe, but if you take large steps, it overshoots. And then the solution to this is that we need to smooth the landscape. And this is done by these normalization techniques, such as batch normalization. So what batch normalization does is it normalizes the activations to zero mean and unit variance at each layer before every gradient step. So here you can see in the equation that we subtract the batch mean and divide by the batch standard deviation. Plus some tiny epsilon to avoid the division by zero. But we still want to keep the the learnability of the network, right? The expressibility of the network. So we also learn this scaling and shifting parameters, gamma and beta. So these are completely scalable, and these keep the expressibility of the network intact, even though we're constraining the activations to be zero mean and unit variance. Okay. So the side effect of this is also that since this mean and variance come from every random mini batch, this also acts as mild regularization and helps with generalizing the model, which we'll talk more about generalization later. But batch normalization also helps in more generalizability. Yeah, this is the PyTorch code for it, and yeah, the next thing we'll talk about is layer normalization. But before that, we also want to talk about how does batch normalization actually smooth the landscape. So without normalization, you can see that a weight update or change in layer L changes the magnitude of the inputs to layer L plus one, right? So imagine you change in layer 5, say 6, 7, 8, 9, and all the downstream layers get affected in an unpredictable manner. Right? By renormalizing after each layer, saying no matter what the earlier layers do, the input distribution to the subsequent layers will always be zero mean and unit variance, right? So the layers are sort of decoupled, and each one, we're enabling each one to see a stable input regardless of what has happened before, right? So this is how the sort of loss landscape is smoothened. Okay, so the next thing we'll talk about is a layer norm. So this is the same concept as batch normalization, but essentially instead of normalizing across the batch, we normalize across the different axes, across the features per sample, right? It's the same formula, just the only difference is the computation, right? In batch norm, we computed across the batches, so we need large batch sizes. But in say sequential models, say like transformers or RNNs, right, but the sequence size may be different, may not be as large, then what we do is we take the sort of statistics across the features for the one sample, right? So this works regardless of the batch size. So this is layer norm. And yeah, we'll just look into why does batch norm work, right? So the original paper actually said that this works because it reduces the internal covariate shift, right? It reduces the shifting distribution of the layer inputs. But now it's a sort of considered an incomplete explanation. The more current understanding is that it makes the landscape smooth, which is what we talked about, right? It makes the loss surface more Lipschitz continuous, and that means the gradients change less abruptly, and this enables us to use larger step sizes and leading to faster convergence when we're optimizing. So you can check out these papers for some further reading, right? Okay. The next thing we'll talk about is generalization, right? This is the last topic. How do we prevent the model from overfitting, right? So what do we mean by generalize? So, I mean, we talked about the loss landscape so far, right? But, and this is trying to, the optimizer is trying to take us to a minima, right? And not all minima are the same, right? This whole landscape might have multiple minima, and some might be very sharp and narrow, and some might be wide and flat. Right? So when you've reached a minima, imagine you're at a sharp, narrow minima. Any small perturbation in the weights and the inputs can cause the loss to spike, right? But whereas when you're in a wide or a flat minima, small perturbations, such as new data, doesn't change the loss much, right? So this solution might be a more stable solution for us to have, and this might be a more generalizable solution. so so this is what we're trying to do using regularization, right? We're trying to make the optimizer move towards wider and flatter minima that provide more stable and more generalizable solutions. Okay, so the first method to do this is to penalize the weights. Okay, why do we want to penalize the weights? We want to penalize the weights because large weights would create very complex and sharp decision boundaries, right? And this might fit every training point, but that's not what we want. We would rather fit through a smooth function that is more likely to capture the true pattern, rather than having sharp, complex decision boundaries which are trying to overfit to the noise in the data. So to do that, we want to ensure that the weights that are learned are lower in value, right? Preventing these complex sort of shapes, right? So this penalization is one way to do this, right? So in the loss function, we also add a penalty for the value of the weights, right? To keep the weights small. Now, there are two ways we can do this. Either we use, the absolute values, that is the L1 penalty, right? The sum of the absolute values of the weights, or we use the sum of the squares of the weights. Okay, so that is called L2 penalty. Now, by nature, the L1 penalty, which is called lasso, since it's directly proportional to the weight, the absolute value of the weight, it pushes small weights to exactly zero. So this produces sparse models because the gradient of the penalty becomes lambda into the sign, which is constant in magnitude. Right. So both larger weights and smaller weights get sort of a similar penalty, and smaller weights just go to zero. So this is also used in many feature reduction sort of use cases. Now L2, here the gradient of the penalty is lambda into W, which is proportional to the weight value. So the weights don't get zeroed out. Large weights receive a larger penalty, smaller weights receive a smaller penalty, but they're not really getting zeroed out. Okay, but the model gets more uniform, smaller weights. Now, this is how we would, use it in PyTorch. And the shape plot is just to show how, L1 being absolute of the weight value, it has this, sort of a sharp point. So the weights approach, zero, but this is sort of parabolic. So weights don't really approach zero, right? They don't quite reach it. It's sort of a parabol. Um, okay. The next topic we'll talk about is dropout. So dropout takes a different approach. Instead of penalizing weights, we randomly disable a few neurons during training, right? And here in every training step, each neuron has a probability of being zeroed out by this P is the probability of that neuron being dropped or zeroed out, right? And this division of 1 by P is called an inverted dropout. So it scales up the remaining neurons so that the total expected output magnitude stays the same. So this means that inference time, when all neurons are on, we don't need to use this adjustment. So as you can see in this diagram, different batches has a different subnetwork, right? And how does this help generalization? Because no neuron can become, like a sole contributor to the output, right? And no neuron or set of neurons can be crutch because all the neurons can be zeroed out by any probability. So it encourages sort of codependency, and it prevents any sort of brittle partnerships, and it encourages all the neurons to sort of equally participate in building the output function. So this is on dropout, and the typical dropout probabilities that I use is 0.2 to 0.5, and this is how you would use it in PyTorch. The next one is the simplest sort of regularizer. We just try to stop the optimizer training before it overfits, right? This is sort of the cheapest way to do this. It's called early stopping, right? Whenever we see that the validation loss starts, the training loss is still going down, but the validation loss is increasing, we just stop there, right? So it's essentially trying to stop it where it's at a point where it's trying to memorize too many details of the training loss that is not really helpful on new unseen data. Okay. So quick summary on regularization: we covered methods that help us penalize large weights so that we can get a smoother boundary that involves L1 and L2. Then we talked about dropout, random neuron removal. We talked about early stopping. And in the previous chapter, we also talked about batch or layer normalization, how it also acts as mild regularizer. Um, and yeah, we would ideally, when training a neural network, we would use multiple of these together because they address different failure modes. So overall, so far we covered initialization. We covered, why initialization matters, what would be the objective for an initializer, and how different activation functions require their own corresponding initialization methods. Then we talked about, how do we, during backward pass, how do we ensure that the gradient signal does not vanish or explode? So we talked about gradient clipping, skip connections, residual connections, ReLU activation function, and so on. We also talked about other ways to stabilize training by smoothing the loss landscape, and this was batch normalization and layer normalization methods. Then we talked about regularization. So regularization methods we covered L1, L2, dropout, early stopping, and so right. Okay, so this is the end of the training deep neural networks module. Okay. Hi, everyone. This module is going to be about CNNs, convolutional neural networks. These are the building blocks and the major architectures that made deep learning work for computer vision. Okay. So we'll cover two things in this agenda. The first one is CNN building blocks, what convolution actually does, and different concepts such as padding, stride, pooling, and receptive fields. Then we'll also cover some of the key architectures, how they've evolved, and some applications. Okay. Let's talk about CNNs in production at scale, right? Let's talk about a lot of the applications specific, especially to Amazon, and what would be the goal or what would be the use cases for these kind of networks. So one of them could be the product image classification, right? We try to use the product images to automatically categorize sort of millions of products into their taxonomies, detecting image quality issues and so on for the listings. The second thing could be visual search, right? So you take a picture, take a photo of an item, and the network is already able to extract the visual features and then match them with other products, right? So retrieve similar products from our catalog. The next thing would be fulfillment center robotics, where we need a lot of object detection and segmentation for the robotic picking, right? Edge detection, identifying item boundaries, where to cross the arm, in reading the package labels in real time in the conveyor belts and so on. The fourth thing could be also content moderation. So, detecting sort of policy validating images across the listings and so on. And so these are a few sort of real world applications. So with this sort of goal in mind, let's go ahead to see how these sort of CNN models are built specifically for images. Okay. Um, so let's start with the building blocks of CNNs. So why do we really need a new network called CNNs for images, right? So images actually have a new spatial structure that the traditional fully connected layers just completely ignore, right? So what do we mean? So one thing is, say a image is uh, depending on the pixel size, is 224 and 224 to 3 for RGB, has about 150,000 pixel values, right? So just one image. And one hidden layer of 1,000 neurons requires over 150 million parameters for just that single layer, right? So that's one reason. The second reason is there's no translation equation. So, how would we pass an image to a deep neural network, right? We would just sort of vectorize it, and then what the MLP would do it would treat a cat in the top left corner as an entirely different pattern from the cat shifted to the bottom right. Right? It doesn't sort of really understand this translation through the image. The second thing is there's no local structure, right? There's no way that the model understands that these pixels are near the first pixel, right? And then, sort of adjoining. So these should be considered together. They're forming some sort of image or a concept together. And maybe and this could be not just for neighboring, neurons, but also, say, for example, if there's a border along the corner of the image, that should be considered, as sort of one concept, right? So the different pixels are sort of equally, related, and when we pass it through a fully connected layer. But here we want to make the model understand that nearby pixels actually share more information, right? And far away pixels probably share lesser information. So that's more about the structure of images. So this convolutional neural network is mainly to make the model understand these underlying structures in an image, right? Which we call inductive bias that we want the model to have whilst it starts training. So the first one is locality, second one is translation equivariance, and third one is compositionality. Right? So compositionality means, that complex features are built from simpler ones. Say, for example, there are, different parts of, a face in an image, and it's, overall building one image, right? So that's compositionality part. That also comes with understanding the sort of structure. Okay. Now, how does convolutional neural networks solve this? So convolutional neural networks primarily use this thing called the convolution operation, right? So this is the core operation where you have a small grid of weights called a kernel or a filter, right? And this is the primary parameters set that we are learning. Okay, and we slide this kernel across the input image, and at each position, it computes a weighted sum. So at each position, it computes a weighted sum or dot product of the pixels that this particular kernel covers, right? So for example, here you can see, right? For the first part of the image, this kernel applied to this would give you an output of 5, just multiplying it element wise, right? Then when we step forward, we move the kernel over to the next set of the adjacent set of 9 inputs, and then we get the second output, right? And then so on, right? So then we can fill the entire image through this process. Okay. Now, as you can see, there are two properties that sort of come out here, right? So each output pixel here depends only on a small region of the input. Okay, and the other one is the weight sharing. So the same kernel is applied at every position. So this allows to have fewer parameters, right? Okay. Now, one thing you might have noticed is we started off with a 5 into 5, sort of input size, but then we ended up with 3 into 3. Right? So obviously, when we're moving with these kernels, there is, some loss in the size with each step, right? And this is where, this concept of padding also comes, which we'll sort of talk about in more detail. But when you slide a kernel across an input, the output is either smaller in size, depending on how the kernel size is. And this formula is a formula to calculate what would be the output size. And it depends on the input size, the kernel size, how many paddings, the zeros added per side, and what is the stride. So, for example, imagine we take an example of, same padding. Right. So we start with input size 32. We use a kernel size 3, and we add a padding and stride of 1, and we get output size same as 32. If we take a stride of 2, which means we move the kernel 2 steps, then we get an output size of 16, which is halved. Right. So this is just a useful formula to quickly calculate the output size and adjust the padding, stride, and kernel size, etc., accordingly as we want the output size to be. Okay. So let's talk a bit more about this padding, right? So padding is essentially the zeros that we add around the input border to control the output size and preserve edge information. Okay. So essentially, a valid padding is no zeros. The output always shrinks. The border pixels then participate in only fewer computations, only in their own. So the edge information gets progressively lost the deeper we go into the network. The next type of padding is same padding, right? We just add just enough zeros, which is comes out to be floor of k by 2 when k is odd and the stride is 1. So the output has the same spatial size as the input. Every input pixel appears in at least one output computation, and so the spatial information in the borders is preserved. This is what most modern networks use. Okay. And the practical impact is that without adding padding, a 224 into 224 layer image loses 2 pixels per convolution layer, right? And after 5, say 3 into 3 convos, it's down to 214 to 214, and you've lost all the context about the border. With the same padding, the dimensions stay 224 into 224 until you explicitly choose to downsample the image. Next is stride, right? So stride is how many pixels the kernel moves at each step. So a larger stride produces a smaller output. Okay, and stride equal to 1, the kernel moves 1 pixel at a time. So it has maximum overlap between the adjacent input fields, and the output dimensions are approximately the same as the input, right? With stride equal to 2, the kernel skips every other position, right? So the output is roughly half the input size in each spatial dimension. So this is a efficient way to also downsample feature maps. And in modern architectures, they mostly use a stride to convolutions instead of pooling or any other methods for downsampling. Okay. Now, we just mentioned pooling. What is pooling, right? Pooling is especially when we want to downsample, we can either do a max pooling or average pooling through a particular kernel size, right? So here there's no learnable parameters. So for example, if I do max pooling of each part, I get a max of each of these 2 into 2 size. And with a stride equal to 2, I get output of 2 into 2. Okay. If I do an average pooling, you can see I get the average of each of these kernels. And again, because it's stride 2, I get an output of 2 into 2. Okay. So max pooling takes essentially the maximum value. So it's you're trying to keep the strongest activation intuitively, the most detected feature. In average pooling, you get a more of a smoother summary, right? And this global average pooling is sort of commonly used as the very last step before classification models, right? It replaces the large, fully connected layers. The next concept relevant to CNNs is something called the receptive field. So this is essentially the region of the original input image that a single neuron in a deeper layer can see. Okay, so that influences the part of the input original input image that actually influences the a particular output value. Okay, so I'll show you a quick interactive demo here, right? So if I click any neuron here, you can see the receptive field of this, right? So essentially, where did this output come from, right? Which are all the original input image pixels which contributed to this particular output. Okay, so here, there's a key insight for how do we design architectures, right? So if we stack 3 into 3 convolutions, they give the same receptive field as a single 7 into 7. It both see a 7 to 7 patch. But 3 and 3 layers use about 50% of the parameters or 55% of the parameters of a single 7 to 7 sort of a layer, right? While adding extra non-linearities as well. So it's more expressive and fewer parameters. So this is why modern architectures use small kernels, but they're stacked deeply. Right, and the general formula for receptive field computation is sort of shown here. Each layer adds k minus 1 times the product of all the preceding strides. Okay. Now, let's talk about what a typical sort of convolution block looks like. Okay. So the standard building block you'll see repeated in nearly every CNN goes as follows, right? So you typically have a convolution block, then a batch norm, then a nonlinear sort of activation, then a max pooling. Okay, so the idea behind this is that the convolution extracts features, the batch norm stabilizes them, the ReLU adds some nonlinearity, and the pooling, downsamples it. So this, you also see the PyTorch code here is pretty straightforward. And this is sort of a common pattern. The spatial dimensions half while the channel depth doubles in each stage. Now let's talk about the CNN architectures, how they've evolved over a decade, right? So starting from the LeNet in 1998, this proved that initially the CNNs work, right? Then we go to AlexNet in 2012. This is the main ImageNet movement that launched sort of a modern deep learning with GPU training, ReLU, and dropout with 60 million parameters. Then we went to the VGG 16, which went deep with uniform 3 into 3 filters and 138 million parameters and 16 layer depth. The next one was the GoogleNet. The same year went wide instead of deep with parallel branches and drastically fewer parameters. So this was sort of an interesting way to do it with wider networks, and it's called an inception module. We have multiple parallel branches. And then we have ResNet, which went extremely deep using skip connections. And so this is the has been the sort of gradual evolution. The networks have gotten deeper, but also smarter, and more depth doesn't require more parameters, as you can see. If you design the architecture well, especially with ResNet, as you can see, the depth is 50, but it's still uses lesser parameters than AlexNet and VGG, right? Okay. Um, Yeah, so just covering a few, additional points here. So VGG's main contribution is, they had two stacked 3 into 3 convolutions over the same receptive field as one 5 into 5, right? But with fewer parameters and an extra nonlinearity. So this is why no modern architectures use large filters. So this is the key insight that we got from VGG. The inception insight, as you talked about, the key contribution is they run multiple filter sizes in parallel. So use one-into-one convolutions as bottlenecks to control computation. And the result is that they were able to get a 6.8 million parameters with better accuracy than a 60 million parameter AlexNet. Right. And finally, the ResNet's contribution was primarily on the skip connection. Okay, means that the gradients always have a direct identity path, and this we had talked about in previous modules as well. So this unlocked training networks with 50, 100, 152 layers due to the skip connection. And this is the sort of ResNet block diagram here. So the input goes through two convolution layers, but also bypasses them directly to an addition node. And that bypass is the primary, sort of innovation that enables deeper and deeper networks. Okay. Now let's, talk about, some more intuitive concepts to where parameters actually live in a CNN, right? So if we talk about a single filter in a CNN, it's not actually 2D, but it's 3D, right? A 3 into 3 filter applied to an input with 64 channels is actually comes out to be 3 into 3 into 64, which is 576 values plus one bias. So if we apply 128 such filters, we get about 74,000 parameters for that convolution layer alone, right? So convolution layer formula, it comes out to be the number of filters times so f into the number of input channels plus the one bias per filter, right? Now, if we compare the VGG's first fully connected layer that we were talking about, takes 7 into 7 into 512 volume. That's 25,000 values and maps to 4,000 neurons. That single fully connected layer has over 102 million parameters. So one fully connected layer has 1,400 times more parameters than a convolution layer that does more spatial processing, right? So this is the primary innovation that we got from a primary benefit that we got from convolution layers, especially for image structure type processing, right? And this is also why modern architectures have replaced, large fully connected layers towards the end of the CNN with global average pooling. right? So this reduces the FC portion of parameters from, about 120 million parameters in VGG to about only 2 million in ResNet as well, right? Okay. Now, okay, let's also talk about this one-to-one convolution that we had mentioned earlier, right? So what's the point of this? It doesn't look at, spatial neighbors at all. So first use of this is channel reduction. So before applying an expensive sort of 3x3 convolution on 256 channels, we first reduce that to 64 channels with 1x1 convolutions. Only 16,000 parameters for that reduction, and then 3x3 operates on 64 channels instead of 256. The second use is adding non-linearity, right? A 1x1 convolution followed by ReLU as a nonlinear transformation without changing the spatial dimension. The third use is cross-channel interaction. At each spatial position, it's a learned linear combination across all channels, right? So like a tiny per pixel sort of fully connected layer. And yeah, this comparison also shows this clearly, right? A one-to-one bottleneck is 16K params versus 590K for a fully connected sort of layer. Okay. Or sorry, 590K for a full 3x3 sort of convolution, right? Okay. So this one-to-one convolution now started appearing everywhere in inception modules, ResNet, bottleneck, blocks, and so on. So it's primarily like a dimensionality reduction step, right? Okay. The next part we'll talk about is transfer learning. So in industry, you almost never train a CNN from scratch, right? So a huge part of CNNs is reliant on transfer learning. So the one thing is feature extraction, right? Now we freeze the entire pre-trained network, just train a new classification head on top, and this works remarkably well with even with very few examples, because the convolution layers already knows what edges, textures, and object parts look like, right? So having a pre-trained module trained on such a large data set like this ImageNet data set helps these layers learn general visual features, and then we can use them for new tasks with very less data. And the next concept is fine-tuning, where we unfreeze the last few convolution layers and train them with a small learning rate, right? The earlier layers keep the generic, edge and texture information that they've already learned, where the later layers adapt to the specific domain that we are fine-tuning for. Then there's full fine-tuning, where we unfreeze everything but use a very small learning rate. This is only when we have substantial data to train on, and if the domain is quite different from, say, ImageNet. The code is pretty minimal, 3 lines to load pre-trained weights and then swap the classification head and, maybe freeze layers. So the key takeaway is, we almost never train a CNN from scratch. We always want to start from pre-trained weights on, that's trained on any visual task. Okay. Then object detection basics, right? So we talked also about object detection when, we talked about use cases. So there are 3 levels to this. One is classification, what is in the image. So for the whole image, it gives us, one label. The next is, localization, right? So localization is, where is the object? So you need additional output values, like say some X, Y, and widget and height, for one bounding box. And then the next one is detection, right? Where are all the objects, right? So you want to identify all the objects in image, multiple boxes, bounding boxes, and classes, and then confidence for each, and so on. Now, here IOU, intersection over union, this measures the detection quality. So essentially the area of overlap divided by the area of union between your predicted box and the ground truth. Okay. And the YOLO approach is you only look once. So you essentially divide the image into a grid, and each cell predicts bounding boxes and class probabilities in a single forward pass. Right. So there's no separate region proposal step. So this helps make it real time. Then there's also non-max suppression. So this handles duplicate detections. You keep the most confident box, suppress anything that overlaps it heavily, then repeat for the next, highest confidence box until all boxes are either selected or suppressed. This is what powers robotic picking and fulfillment centers, package label reading, and content moderation, where we need to find the specific sort of violating region. Okay, so this is a few sort of concepts regarding object detection use cases. Okay. The next one we'll talk about is neural style transfer, right? So this is combine the content of one image with the artistic style of another. So here we use CNN layer activations as the representation. So this is more of a creative application that also tells us something deep about the CNN representations. So one of the concepts here is content loss. At a chosen deep layer, the activations for your generated image should match those of the content image, right? Deep layers encode what objects are where without caring about the exact pixel values. Then the next one is the style loss, right? So instead of comparing the activations directly, compare the gram matrices. Okay, this is a correlation between the different channels. So if channel 5, which is say about vertical edges, and channel 12 is about say blue color, if they're correlated in the style image, then they should be correlated in the output as well. So this captures texture patterns without caring about spatial layout. Now, think about optimization. The optimization has been unusual. So the CNN is frozen. You back propagate through the frozen network into the pixels of the output image itself. You're optimizing the image instead of the model weights. This is another way to do it. So you start from the noise or the content image and then back propagate into the output pixels directly. Only the image pixels are updated. Okay, so all of these concepts show why pre-trained CNN features are so powerful. It provides sort of a universal perceptual representation of image content and style and so on. And the same features used for classification also define are able to define content and style in a meaningful way. Okay. So let's talk about the key takeaways from this module on CNN. So CNNs exploit spatial structure. That's what we talked about is the innovation in the convolutional neural networks versus the fully connected networks. They exploit locality, weight sharing, compositionality of structures such as images, and the standard block is convolution, batch normalization, ReLU, and pooling. The other one that we saw, especially from the evolution of architectures, is the architecture design itself seems to matter more than the parameter size. So smart architecture designs, such as skip connections, can help us go deeper. The 1x1 bottlenecks cut computation, and small filters that are stacked, beat deep large filters. Transfer learning is the default. We also talked about this. Pre-trained features are general, so we take pre-trained models all the time and then fine tune for a specific task. You almost never need to train from scratch for a particular task. Then the other thing that we talked about is CNNs powering detection, generation, and search. Right, so the same convolutional features can serve classification type applications, localization, object detection, and style transfer, visual similarity, and so on. Okay, so that's the end of the CNN module.